Okay, good morning, everyone. So welcome to the third lectures of Math 2301. So today we are going to talk about floating point numbers. Okay, so we will define what is a floating point numbers, and we will explain, what is the errors between the real numbers and the floating point numbers. So roughly speaking, suppose you have a real number like pi. When you store into the computers, you cannot store pi exactly. You have to store like 3.1415, something like this. Okay, so it causes the errors, and we will talk about it. So, and then there are some consequences, and one of the consequences is the catastrophic cancellation. Okay, so hopefully we have time to cover this. Okay, so now, so this one is, a pictures of the motherboard with the CPU. Suppose you open up your desktop. Okay, so this what is you can see inside the computer. This is the motherboard, and the fan here underneath the fan is a CPU. Okay, and this one is when you put some memory card. Yeah, and this one is the connection to outside devices. But anyway, so what we focus is how does the MATLAB or how does any scientific program do some calculation inside the CPU. Okay, so inside the CPU, okay, under the fan, yeah, then you have a CPU, and inside the CPU, if you have studied computer science, you will know that inside the CPU they have other components as well. Okay, so they have some register, yeah, and then they have some some unit. ALU stand for arithmetic logic units, and some register when they store temporary results. But what we are focused is the green blocks. So the green blocks is the floating point units. Okay, so where all the floating point calculation occurs. Okay, and now you know that inside the computer, one register, yeah, one register like this is divided into what they call the bits. Yeah, the bits is the smallest units inside the any electronic circuits that represent 0 or 1. Okay, and from that representation, then you can represent a number. So this is a general definition. So I will explain by example before we go back to the explanation. So suppose you have number 50. Okay, so then what you have is like let me write down somewhere here. Yeah, so so suppose you have number 50. Yeah, so maybe let me write in the whiteboard. Okay, so share the screen and I share a whiteboard. Okay, so suppose you have a number 50. So this one is decimal numbers. Okay, but you can write this as binary numbers. Okay, so have you heard of binary numbers before? COM1521. Yes. Okay, so maybe you've seen it before. So now how do you find the binary numbers of 50? remember how do you, so you just keep divided by 2. Okay, so say if I divided by 2, then I got 25, right? And the remainder is 0. Yeah, and then I keep divided by, so the remainder is 0, and then I keep divided by 2, then I got 12, right? And the remainder is 1, and I divided by 2, got 6, so remainder is 0, and 3, then 3 divided by 2 give me 1, and then 3 divided by 2 give me 1, right? And then the last remainder is 1. Okay, and then so now you get the digits back. Yeah, so you got like, so how do we get the number? So we got 1 1 0 1 0. Okay, in binary. Okay, so what it means is, so this one just means that it's 0 here. This one just means 2 here. Yeah, so 1 here stands for 2 to the 1. Yeah, and this one you got 2 to the 2, and this one 2 to the 4. So 2 to the, sorry, 2 to the 2, 2 to the 3. So you got 8 here. Yeah, and then here you got 2 to the 4, you got 16. Yeah, I think we missed something. I think maybe we have to, when we divided by 2, we got 0 here, so we have to put a 0 here. Yeah, so we forgot the 0 here. So actually then the full number should be something like this. Okay, so let me do the calculation again. Yeah, so you see that this one is 0, power 1, power 2. So 0, power 0, power 1, power 2. So power 2 is 4, right? This one should be 4. So this one should be, I should be able to draw it. So, okay, so this one should be 4, right? So 0, 1, 2, so 4. And this one 5, 6. So 2 to the 6 is 16, right? And then the last one is 32. So 32 plus 16 plus 4 is 50, right? So this, wait, 16 plus 4 is 20. Why got so what's wrong? 1 1 0 1 0. So maybe we do some wrong calculation here, but 1 1 0. So the correct should be, okay, so good afternoon everyone. So welcome to MATH2301 for
sorry.
term 1, 20.
Oh, sorry, what is the,
and I'm
sorry, somebody just turn on some videos.
So everything is okay, right? Okay, so go back to uh, 1100. I think we missed a 0. So 50 you divided by 2 is, yeah, the remainder of, okay, so we missed one column. Okay, so let me do this calculation again. So this one should be 50 you divided by 2, then you got 25. You got 25 and you divided by 2, you got 12. This one should be 0, yeah. So I think we did something wrong here, yeah. So this has to be done carefully. So 50, 25, 12, 6, 3. Okay, so we need to just adjust the 2 column. Okay, so now just erase this one, yeah. So this one is 0, then it's correct, yeah. Then so 25. So this one should be 1. Remainder is 1, yeah. And then this one is remainder is 0. Okay, so remainder is 0 and remainder is 1. Okay, and then you got 1 and then you got 0. Okay, 25 divided by 2, right? Then the remainder is 1. Yeah. Okay, so sorry, the last one is not the last one is not 0. The last one is 1. I haven't got my coffee, so but anyway, so now, yeah. So the second column is a remainder. Okay, so remainder when you divide it by 2. Yes, you use a remainder to encode the binary form exactly. So essentially, you got 1 1 0 0 1 0. Okay, is the binary representation of 50. Okay, so you can check. So this one is mean that 2 to the 0. This one is 2 to the 1 is 2. 2 to the 2 to the 3 to the 4. So this one should be 16, yeah. And this one should be 32. Okay, so you see, so this one is 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 3, 2 to the 4, 2 to the 5. Okay, so this one 18 plus 32 is 50. Okay. Do you always take floor n over 2 mod 2? No, you take n, you modulo 2, and you take the remainder. That's the algorithm. So we will discuss how we get this algorithm. Okay, but for the moment, just see that 50 can be represented by this binary number. Okay, but this binary number can be written in many forms. Okay, so remember you have say 123, right? So this one I go back to the decimal. So 123, then you can represent by 1.23 multiplied by 100, right? So So this is a simple calculation. Okay. So now, so 10 here is a base, right? And this one is like the fractional. I mean, not the fractional, but it's like you represent 1, 2, 3 by just floating numbers. Yeah. So you can do the same for binary. Instead of writing 1, 1, 0, 0, 1, 0. Okay, I can write. So okay, so now I go to the. Can you put binary digits as an element in a vector, and then dot product? Yeah, exactly. Yes, 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 yes. So in the case of a binary, I can do the same. So I got 100. Well, not 100, but you know, I mean, I just move the dot. Okay, 1, 2, 3, 4, 5. Yeah, 5 places. Then I say that multiply by 2 to the 5. Okay, so this is my previous number, but I just write it in terms of a fraction. So why do I do this? Okay, so I will explain in a second, but let we just see that this is, you know, what we call a floating point numbers. Yeah, and now for numbers bigger than 1, then you can write, you can use this algorithm to find the boundary representation. But how about say 0.5? Okay, so say suppose for 0.5, how do you represent this one by a binary number? How do you represent this by a binary number? Yes, it's just 0.1, yeah, in binary form. And this one, you know, I mean, it can be understood as after the dot, you just take 1 divided by 2, right? And similarly, you can represent like, so what is 1? I mean, sorry, 0.11. Okay. Then what is this number? It's just 1/2 plus 1/4. Yes, because see now, I mean, you move. Yeah, so 1/2 plus 1/4 is just 0.75. So you see that binary number can be used to represent decimal bigger than 1 and less than 1. Okay, so that's the whole point. So now I go back to the slide. So we are going to somehow give a general formula. Where is my slide? So I'm going to give you a general formula for this. Okay, so what we call a floating point representation is a number of this form. Okay, so just forget about the notation, but you know, D0, D1, D2, D3 are just digits, and in the computer they're just binary number. I mean, only 0 or 1, you know. But in mathematics, you know, you can give a very general definition. B can be any base, you know, can be 2, can be 10, can be 60 if you are from the Mayan civilization, you know. But anyway, so now DJ, we call it a digits. Okay, and then exponent. So remember in the example I have exponent 5, so we call it exponent. And does B have to be an integers? Very good point. B should be an integers, yes. Okay, and S is a floating numbers, yes. So no, sorry, X is a floating number. X is a floating number. And it is written like this, in this form. So remember, we wrote 50 like 1.01 something multiplied by 2 to the 5, 2 to the 5th, yeah. So that is exactly this form. Okay. And E exponent. And then there is a term called normalize. Again, normalize is if the very first digits is not 0. Okay, so remember 0.5, when I wrote it in binary, I got 0.1. Then it's not a normalized number. Okay, but like 50, then I wrote 1 point something, and it's a normalized number. Okay, so now in MATLAB they have some function that you can convert a decimal number into a binary number. You know, they call it decimal to bin. You can play around with this, and it gives you some way to find the representation. Otherwise, you can find by hand. Okay. So now we did this one already. Okay. So now remember, you know, like this, the floating point representation, you can have infinitely many digits. Okay. Think about like number 1/3. Yeah. You can represent it in terms of you know, 0.3333. So you've got infinite many digits behind the dot. Yeah. So can you give another example? Another example that you can express as a floating point with infinite many digits. Anyone? So give me a floating point representation of a real number that have infinite many digits. Yeah, 1/3 in base 10 already. Yes, and pi. Yes. So pi, you know, is 3.14149, whatever, you know, infinite many digits. So you see, the problem is the computers cannot store infinitely many digits. It has to chop the digits, the number of digits, you know, at some point. And that is I'm confused for 0.5. 0.5 is not normalized because, well, actually, when you wrote 0.5, yeah, it's not normalized form. But when you write 5 multiplied by 10 to the minus 1, then it's a normalized. Okay, so does that make sense? So normalized, it just means that the way you write so that the first digits is non-zero. So you write 0.5, then it's not normalized, but you write 5 multiplied by 10 to the minus 1, then it's a normalized number. Okay. Okay, so now go back to the floating point number system. So then, because you know, you cannot store infinite many digits inside the computer. Okay, inside, who knows, in the future we might have quantum computer, but that's a science fiction. But right now, what we have, any current, you know, modern computer system, you have only finite many digits in the register, and that's why we chop it at, say, p digits. Yeah, so d0, d1 up to dp minus 1, then you got only d digits. Yeah, and then exponent. So remember exponent, you know, because I mean, in real number system, you can have exponent come from minus infinity to plus infinity, but inside a machine you have to give a range because everything is finite inside the computer, so it has a range from E min to E max. Yeah. Okay, so there's some names, some terminology. So P, we call it precision. Okay, so precision is P, and the range, okay, of the exponent and we call that the range. Okay. And you see now IEEE. So IEEE is acronym stand for, I believe, International something like Electronic Engineers. I forgot, but it's an international organization. Okay. That at the beginning of the 1970s, when they started making CPU, making computers, yeah, then they start to give standard, yeah, and they have two standards: single precision and then double precision. Yes, Institute of Electrical and Electronics Engineers. Yes, thank you. Yes, yeah, Google it. I don't remember. I'm not Google. Okay, so they have two standards. One they call it single precision, and one is double precision. So the double precision use 64 bits, okay, to specify the floating point numbers, and single precision use 32 bits. Yeah, and you see 1 bits can store only 0 and 1. Yeah, and 8 bits become 1 byte. Okay, so then 32 bits become 4 bytes, and 64 bits become 8 bytes. You know, so nowadays what you see is like, you know, in the old days you have Windows 32, and now you have Windows 64. So that is the, you know, underlying that what they use the length of the register to address the memory. Okay, with 64 bits you can represent more addresses in the memory, and that is the remnant from this standard. Okay, and see now, remember the example we have, right? So the S, remember we have the, yeah, we have this format. Yeah, so you have 3 components. So you have a sign, plus or minus. Okay, and you have this part, we call it a significand. Yeah, and then you have the exponent. Okay, so you have exponent E. So that has 3 components, and they will store those 3 components inside the whole register of 64 bits. Okay, so the very first bit they store plus or minus. Okay, the sign plus or minus, and then after that they store the exponent, and then they store only the fractional part of the significand. Okay, so why don't, so remember the significand has 2 parts. Significand has this is a significand, yes, has 2 parts. You have the first digits and you have a fractional part, and they have they store only the fractional part. Okay, is the base always 2 in MATLAB? No, see, in MATLAB there's a floating point numbers. Base 2 is inside the computer, inside the CPU, because inside the electronic circuit, you know, you can have only 0 and 1. You turn on or you turn off the transistor. Okay, so until you have quantum computers. Okay, now in the conventional computers, every bits can be either 0 or 1. Yeah, so that's why you have to use base 2 inside the computer. MATLAB is above that level already. So MATLAB, you know, you can use base 10, you can use base 16, you can use base 2, whatever. MATLAB is a very high level programming language. So, but this one I just explained to you, you know, what is going on underneath MATLAB, and there's some consequences. Okay, when we understand the thing behind. Okay, so now go back to the floating point numbers. So now they store the sign, they store the exponent, and they store the significand. Yeah, sorry, they store the fractional part of the significand, yeah. And then they don't store the leading digits. So D0, they don't store it. So because they assume that, it's a normalized number. So normalized number, then D0 is always equal 1. Yeah. So that's why they don't have to store that. It's a waste of memory. So remember in the 1970, okay, memory are very expensive. So they save 1 bit. It's still a good thing, good saving, you know, and it's carry on until today. So now in the single precision, yeah, in the single precision, exponent is only 8 bits, okay. And then you see, because 8 bits for the exponent, 1 bits for the sign, yeah. Then you got 9 bits already, yeah. So 9 bits, then you got P is 24, right? So what is P? Remember, P is the total number of digits in the 14-point numbers, yeah. And you store only P minus 1 digits for the fractional part significand. So 23 plus 8 is 32, yeah. But in double precision, then you know you have 11 bits for the exponent, okay. And so therefore you have P equal 53. So this means that you have 52 for the fractional part of significand, yeah. So 52 plus 12 is 64. So 64 bits for one single number, okay. So now maybe give ask a simple question. So suppose you store the exponent by 11 bits, yeah. Then what is the range of the exponent you can have? What is E min and what is E max? Roughly 2 to the 10. Why not 2 to the 11? It's very good, but why not 2 to the 11? Yeah, 2 to the 10 is when you have 10 bits, but here you have 11 bits, yeah. So good point, yes. So that's why if you need negative powers, yeah, then you need like to store like only from minus 1024 to plus 1024, something like that, yeah. So that is the min and the max exponent you can have, and you will see it inside MATLAB. So the P is the representative of the number of bits allocated to a fractional part. So remember P in our notation is like this. So D0, yeah, D1, dp minus 1. So it means that, and you don't store D0, so it means that you store only P minus 1 digits, okay. So if P is 53, then I store only D1, D2 up to D52, okay, yeah. So that is just a notation, yeah. And this notation was specified by the IEEE. So now we just, okay, so I will explain about Emacs. I will go back to that more precisely, you know, when we have that that number. But essentially, if you have 8 bits, yeah, then you have only, no, sorry, we have 11 bits, yeah. When we have 11 bits, then you have 2 to the 11 possible choices for the exponent, right? And 2 to the 11 is 400 and no, not sorry, not 400, but 4,000, yeah. So for if we have 2 to 11, then we got 4,000, sorry, 4,000. No, sorry, 2 to the 11 is not 4,000, but 2,048, yeah. 2,048, yeah. So 2,048 choices of exponent, okay. But then if you want a negative exponent and positive exponent, then roughly it has to go from minus 1024 to plus 1024. Okay. If you want to start a negative, and they want a negative exponent as well. No. 2 to the minus 5 is not. You mean like the range? The range of the no. So the range will be no. So well, I mean, if minus 1 to 1023, then yeah, but one, yeah, you want even. Yes, you want even. In 11 bits. You have to distribute evenly between the negative and positive powers. Okay. So but there's other, I mean, if you go from minus 1 to 1023, then you cannot store some number like 2 to the minus 100, for example. Okay. So you have to store some a very small number and some very big number. Yeah. Okay. And now we will see that in MATLAB. Well, before I go to MATLAB, let me explain one last definition. So last definition is, no, I don't say that E min is minus 1024 and E max is 1024. I think that roughly, okay, roughly, if we use the 11 bits, yeah, but they have some special cases. So if you read in the lecture notes, they have some special cases. So that's why the range is slightly different from this one. I don't remember top of my head, but something like a minus 1023 to plus 1093, something like that, because they have some special cases. Okay, but if we don't have special cases, then you can have up to minus 1024 plus 1024. Okay, so now let me explain the next definition. The next definition is the gap between 1 is and the next largest machine number. So suppose, now remember your car, right? Your car, if you drive the car, you see the odometers. So odometers, it has many digits, right? And then if you turn on the last digits, okay, then the gap between when you turn on the last digits minus the current digits, we call it a machine by epsilon. Okay, and machine by epsilon, you know, by this formula, yeah, you turn on the very last digits here. Okay, you minus 1, then you just got 0.0001. Only the very last one become 1. And in the binary representation, just, you know, say b is 2, then 2 to the 1 minus b. Yeah. And now we go to MATLAB. Yeah. So now if I go to MATLAB, I will show you what I'm talking about here. So okay, so now this is my MATLAB. Yeah. So now in MATLAB you can have epsilon. Okay, so epsilon is, remember, the gap between 1 and the next machine number, right? And we just 2 to the minus 1 minus p, and in our case p is 53. Okay, then it gives you exactly the same. Yeah. And now how about E min and E max? So in E min and E max, you will see that in MATLAB or any other language, you know, you can have real max. So real max is this number. Okay, and there's a real mean as well. Okay, so now Now look at this real max. So how do you get this real max? So remember, now you go back to, so go back to the let me go back to the slide. Huh? So if you maybe not this one. Yeah. So now real max, we go back to this. This definition, yeah. Then if real max, then every digits will be equal 1, right? Because think of the odometers. Odometers, the maximum is you turn all the digits into the maximum value you can have. So it will be equal 1. All of them equal 1, yeah. And then E max, I mean the exponent has to be equal E max, yeah. Then that will be the maximal number you can have. So now how do we compute that number? So now we try to compute that number, yeah. So now suppose I try to compute that number. How do I erase everything here? So we try to compute real max. So real max will be, you know, I mean, see whether we can get we can get the same as. So you see my whiteboard, yeah. So real max will be, so now you turn on every digit, you turn to 1, yeah. 1. And then you multiply by 2 to the E max. Okay. And now how do you, well, okay, so now let me look it up. What is E max? We have to look at it precisely. Okay, so now if you again, I gave a very full description inside the lecture notes. If you try to read the lecture note, you will see the value of E max, and there's some special cases. Okay, so now let me try to look up the lecture note and see what is the exact value of E max. So if you look inside the lecture notes, yeah, there are some special cases for exponent, and you will see that E max will be is only 1023, yeah. So for the double precision, so E max is only 1023. So I say that, you know, maximally you can go to 1024, but because there's some special cases, and you can see that special case inside the lecture note, you know, for undefined number, something like that, for infinity, minus infinity, and that's why they have to have some special value. So E max only 1023. So okay, so now if I use this, yeah, then I got 1 plus 1/2 plus. So remember, I try to represent this one in terms of decimal. Yeah. So I got 1/2 1 square plus dot 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 dot. Okay, so what is the last one? What is the last term? What is the power of the last term? So how many digits do we have? 52, yeah. So we have 52. So remember you store 52 digits. Okay. So you agree we have okay, and then we so why 52? Because we have 1, 2, 3 and 52 digits in the fractional part of significant, yeah. And then you multiply by 2 to 1023. Okay. So now what is this number? How do you compute this? So this one is just a geometric sequence, yeah. And then you got 1 minus 1/2 53, yeah, divided by 1 minus 1/2 and multiply with 2 to the power 123. Okay. And so this one will equal 1 minus 1/2 is 1/2. When you flip it over, so it's become 2 minus 2 to the minus 52, right? There's 2 to the minus 53, you multiply by 2, yeah. Okay, so then you multiply by this 2 to the 1023. Okay, so now I want to evaluate this number. So let me do it in MATLAB. Okay, so now if I do it in MATLAB. So remember the formula, right? So 2 minus 2 to the minus 53. So let me share my MATLAB. I will put it in MATLAB, yeah. So if you remember 2 to the 2 minus 2 to the minus 52. You multiply with 2 raised to the power 123. You see, so it equal real max. So real max is 1.7977 raised to 10 to the 308. So you got this. So it's the same. So you see, you understand why. Okay, and then you know the limits. Why MATLAB cannot have a real number bigger than this. Yeah. And the reason why they reserve some special cases for the exponent is because they want to represent infinity and not a number. So that's why we have to stop at 1023. Okay. So you get the idea, right? So any question about this? So real mean. So real mean is very clear. Okay, thank you. So real mean is, again, you set all the digits to be 0. Yeah. But now, why real mean cannot be 0? Because, you know, I mean, real mean, why real mean cannot be 0? It's just a very small number, but it's not 0, it's still positive. And why is that? So this is a subtle point here. So very subtle. So why real mean is not 0? Why the minimal real numbers are not 0, but it's 2.2 10 to the minus 308. Why is that? Yes, because remember, because you store only the fractional part of the significand, and you assume that it normalized number. So the first digit is 1, right? So actually real mean it just, you know, because the first number is 1, so actually just 2 raised to the power of E max, sorry, raised to the power of E mean, yeah. And E mean in so let me double check. E mean in our case will be only minus 1022. Okay, so you cannot go down to 1024 because some special cases. So say real mean, yeah, is only minus 1022. So that's why, you know, they're identical here. So real mean is only 2 to the minus 1022 because real mean is the minimal normalized floating point numbers. Okay, so that's why it's not equal 0. Okay, so now, you know, you can ask yourself that, so how do MATLAB store 0, and how does MATLAB store you know, unnormalized number, and how does MATLAB store infinity or not a number? So please read the lecture notes. Lecture notes explain a bit more details. I don't have time to cover on those things. Yeah, so read the lecture note, and it just explain those you know, special cases. So now go back to the slide. Yeah, so this one so now if I go back to the slide, you a bit confused about what? About the consequence of real max and real mean. 0 is not real mean, but you can still use it in MATLAB. So it's very good point. Yes, when a number bigger than real max, then you just have infinity. Okay, so go back to MATLAB. I share you MATLAB. Yeah, so suppose you take real max, you plus 1, well, not plus 1, but maybe say raised to power 10, then you got infinity. Yeah, so anything bigger than real max, then it become infinity. Yeah, and anything less than real mean, then you know, I mean, it becomes like 0. So essentially now we have to be a bit careful when you got into that range. Okay, so that is the whole point, and we will see it. So now let me show you what happened in the past. They have some consequence of those you know, like misunderstanding about that floating point number. So now go to the slide again. So there was, you know, there was some cases in the past, you know. So there was some documented cases when they somehow they didn't understand a lot about floating point numbers, and it can cause disaster. So for example, the first one is 1/10. So 1/10, you know, when you represent it in binary, okay, then you have an infinite many digits. Okay, and when, you know, they can store only finite many digits, then there's a consequence, there's a errors, right? So the errors. and the errors can be amplified. And in terms of like a military application, so suppose they store a timer is in a register of 24 bits, okay, then you can have an errors is about like 10 to the minus 8. Okay, you can say that 10 to the minus 8 is not big. However, when in a real application, like when you let it run over 100 hours, the errors can be accumulated and it become about half a second. Well, you can say half a second is not big. Okay, it's not big for you, but for say a missile who travel like 1,000 kilometers per second, okay, then it could be a big distance. You see, so this one was a missiles in the Iraq War in 1990, yeah, and it can travel up to 1,600 meters per second. So the error is about 500 meters. And 500 meters in military application could be a huge gap. Okay, so and then there was a case about real min and real max when they didn't apply it correctly. They got underflow and overflow, and it caused a disaster in the space industry. Okay, so when they launch a rocket, back in the maybe in the 1996, yeah, then somehow they misunderstood the conversion between long and short single precision and double precision number, and it caused explosion of rockets. Okay, so you can read this one a bit in the lecture notes. Okay, and then we have to stop here because we run out of time, but you can read the stories in the lecture notes, and there is videos on YouTube explain the incident a bit more. Yeah. So any question? I think I have to stop here because I have a tutorial right after this. So stop recording.